The goal here is to give a proof of this fact that if you've got a group G whose order is a prime P, then that group G is cyclic. What's a nice proof of this? How do you prove something? A group is a cyclic group in general, you have to come up with a generator. You have to find an element A in the group such that every other element in the group is the power of that element A. That's typically how you prove a group is cyclic. Here, it's maybe a little bit easier, you might say. You don't have to necessarily do that. Instead, what you can do is say to yourself, okay, you could think of examples. And in those examples, what you would observe is every non-identity element is a generator. For example, Z5, cyclic group of order 5, is generated by 1. It's also generated by 2, 3, and 4. Those are the non-identity elements, right? Z5 is a group under addition mod 5. The identity is 0. All the non-zero elements, the non-identity elements, are generators. Okay, you should take the time to double check that if you are unsure about that. So it probably doesn't matter what non-identity element we pick. Yeah, that's definitely the case. And you can pick a non-identity element in the first place because prime numbers are bigger than 1, starting with 2, etc. If P is prime, it's bigger than 1. You could, if you want to be extra careful, we could say since P is prime, P is bigger than 1, and there exists a non-identity element in G. There exists an A in G such that A is not the identity. If we want to be extra picky about how we say things, we could say that here. If you just did your proof by saying pick A to be not the identity, that would be fine. I wouldn't mark it wrong. But for a little extra emphasis, the fact that P is prime means it's bigger than 1, means the order of G is bigger than 1. G is non-trivial. So there is at least one element that's not the identity. The claim is that A is a generator of G. The cyclic subgroup generated by A equals all of G. How is Lagrange's theorem relevant? Well, cyclic subgroup generated by an element is a subgroup. By Lagrange's theorem, its order has to divide the order of the group. It has to divide this prime P. There's only 2 possibilities because P is prime, 1 and P. It's not 1 because A is not the identity, so it's got to be P. This has got to have order P. Since G has order P, they've got to be the same thing. Done. You could say something like this. Lagrange implies the order of the cyclic subgroup generated by A is 1 or P, since P is prime. A not equal to the identity means the order of the cyclic subgroup generated by A is bigger than 1. Therefore, the order of the cyclic subgroup generated by A equals P. Again, if we want to be extra picky about things, we know that the cyclic subgroup generated by A, since A is an element of G, would be a subgroup of G. The order of G equals P, the order of that cyclic subgroup equals P. All these things imply that the cyclic subgroup generated by A must be all of G. We're done. Praise the Lord.